Hello everyone, welcome back to yet another talk on Semiva on the session of Spectral Algebraic Geometry. Today we have Federico Mocchetti who will present us about Tannaka duality for spectral algebraic spaces. So please go ahead.
Okay, thank you Krishna for the introduction and thank you everyone for being here. As said, today's seminar is on Tannaka duality for spectral algebraic spaces. So first things first, what is a spectral algebraic space? So a spectral algebraic space is a spectral Deligne-Mumford stack X such that for every commutative ring R, the mapping object from the étale spectrum of R to X is zero truncated with respect to the homotopy structure. In other words, it is discrete. First example, if you start from any connective E infinity ring A, then the étale spectrum of A, spet A, is a spectral algebraic space. In particular, we are interested in quasi-compact and quasi-separated spectral algebraic spaces. Now, these two notions are totally analog to those defined for classical schemes. In particular, quasi-compact means that every open covering admits a finite refinement, and quasi-separated is a condition on the diagonal. So the diagonal map is quasi-compact, which means that the pullback along the diagonal preserves zero coherent object, where an object is said to be zero coherent if the topos x over u is quasi-compact. And as I said, this has strong analogies with the same notions defined for usual schemes. Now, if we start for a spectral algebraic space and we consider the functor represented by it, so given by the Ionet lemma from connective commutative algebras to spectra, then one can see that this functor is quasi-geometric. So we can apply to this functor Tannaka duality for quasi-geometric stacks, and in particular, X can be recovered from the symmetric monoidal infinity category of quasi-coherent sheaves on X, together with its T structure. And the goal for today is to show that this extra information given by the T structure, which we usually need to recover an object X from quasi-coherent sheaves on it, is unnecessary in the case X is a qcqs spectral algebraic space. Now, this may seem a bit vague, but we will make it clear later. In particular, the main result of the day will be this theorem, which is numbered 9.6.0.1 in spectral algebraic geometry. And the theorem goes like this. So let X and Y be spectral Deligne-Mumford stacks with X a qcqs spectral algebraic space. Then we have a fully faithful embedding theta from map in spectral Deligne-Mumford stack from Y to X to this category of symmetric monoidal functors from quasi-coherent sheaves on X to quasi-coherent sheaves on Y, where this theta is simply given by the pullback. Now, the essential image of this functor can be characterized in the following way. So the essential image is spanned by the symmetric monoidal functors that preserve small colimits. The goal of today, as I said, will be to prove this theorem. In what sense does this theorem allow us to reconstruct X from the category of quasi-coherent sheaves on X? This sense is given by this following corollary, which is numbered in spectral algebraic geometry 9.6.4.1. And it goes as follows. So let F from Y to X be a morphism of qcqs spectral algebraic spaces. If the pullback map induced by F from quasi-coherent sheaves on X to quasi-coherent sheaves on Y is an equivalence of infinity categories, then also F is. And so in this sense, we can reconstruct X up to equivalence from qco over X. This corollary follows like rather immediately from the theorem, because I mean, if both X and Y are quasi-compact, quasi-separated spectral algebraic spaces, then one can essentially apply this construction in both directions, and so one get like description like of the essential images, and so like let's say one gets a description of the mapping objects from Y to X and from X to Y. Okay. Now, to prove this theorem, we'll need some preliminary results, and in particular, we will have to dive a bit into the world of perfect stacks, which we did not cover in our lectures. But yeah, let's say a couple words on perfect stacks. So a functor X from connective commutative algebras to spaces in this case is called a perfect stack if it is a quasi-geometric stack. The structure sheaf OX is a compact object in quasi-coherent sheaves, and each object in each quasi-coherent sheaf on X can be obtained as a filtered colimit of perfect objects. So you can write that quasi-coherent sheaves on X is the int category of perfect objects in quasi-coherent sheaves on X. What is a perfect object? Now, this is a bit of a technical notion. We will not really need it, but for the sake of completeness, now recall that quasi-coherent sheaves on X can be seen in general as a subcategory of left modules over the structure sheaf OX. This notion of being a perfect object is defined in general for any left module over OX, and we say that M, such a module, is perfect if it can be obtained as a filter diagram of objects in this subcategory. If for every filter diagram of objects in this subcategory, then this canonical map between these let's say X functors is injective when the index is equal to 1 and is bijective for the index strictly smaller than 1. Okay, I mean, whatever, we will not really delve deeply into this condition. Why do we care about this perfectness? Well, a first nice result about perfectness is given by this lemma, which I call A, and this a sum of these two results from spectral algebraic geometry, so 6.2.6.2 and 9.1.5.5. First result is that given any functor from connective commutative algebras to a large category of spaces, and given F quasi-coherent over this functor X, then we say that that there is this equivalence between F being perfect and F being dualizable in the category. In the case X is a qcqs spectral algebraic space, and F is always a quasi-coherent object on X, then we have that F is perfect if and only if F is a compact object, where I recall that the compact object is such that the Yoneda embedding on this object preserves filtered colimits, whatever. In particular, this equivalence between F being perfect and F being compact implies via this result 9.1.5.3 that for X qcqs spectral algebraic space, the structure sheaf OX is compact. Okay. The first result we will be interested in and that we will prove is this proposition B, numbered 9.6.1.1 in spectral algebraic geometry that goes as follows. So let X be a qcqs spectral algebraic space, then the category of quasi-coherent sheaves on X is compactly generated, which means that it is presentable and omega accessible where omega is the first infinity cardinal. And moreover, X is a perfect stack. Now, if you go back to the definition of perfect stack, you see that, we already said that the functor represented by a spectral algebraic space is quasi-geometric in the beginning. We just saw that the structure sheaf in this case is a compact object. So actually we will just have to prove this condition C. Okay. So our first goal is to prove this proposition B, which will be which is useful to prove our theorem in the following sense. So as I told you, there is a theory of Tannaka duality for perfect stacks, and it actually was already developed before spectral algebraic geometry. In particular, this result that I'm mentioning now comes from results of Bat and Halpen-Leissa. Now, as we saw, if we start from X, a qcqs spectral algebraic space, then we get a perfect stack. So what I'm going to state now is the Tannaka duality theorem, let's say, for perfect stack by replacing X perfect stack with X qcqs spectral algebraic space. And this reads as follows. So let X be a qcqs spectral algebraic space and let Y be any spectral Deligne-Mumford stack. Then this assignment, this map we already saw before, this theta from maps in spectral Deligne-Mumford stack from Y to X to symmetric monoidal functors from the quasi-coherent sheaves on X to the quasi-coherent sheaf on Y that sends F to its pullback. This map determines an equivalence between the first category and the full subcategory of symmetric monoidal functors spanned by the right T-exact colimit preserving symmetric monoidal functors. In this sense, if you remember in the beginning, I said we want to prove that for spectral algebraic spaces, qcqs spectral algebraic spaces, Tannaka duality is independent of the information coming from the T structure. The goal will then be to prove that this right T exactness is not a condition to impose on the essential image, in the sense that what we will prove is that the functors appearing in the essential image are automatically right T exact. Okay, let's go on with this fact, which we are not going to prove, but that will be necessary, as you see before, to prove proposition B. Fact is numbered 9.6.1.2 and reads as follows. Let X be a qcqs spectral algebraic space and let C be the subcategory, the full subcategory of quasi-coherent sheaves on X spanned by the perfect connective sheaves. Then the inclusion of this subcategory extends to an equivalence between the int category of this C and the connective quasi-coherent sheaves on X. And as I said, we're not going to prove this proposition, but you can find the proof in spectral algebraic geometry. Having this result, we can proceed to the proof of proposition B. And we will adopt, like, I would say, usual, a rather usual technique in category theory. So let D be the subcategory, the full subcategory of quasi-coherent sheaves on X spanned by the perfect objects. Now, as perfect is equivalent to compact, as we said in fact A, then this inclusion extends to a fully faithful embedding, which we call theta, from the int category of D to the whole category of to quasi-coherent sheaves on X. And we can characterize the essential image of this theta in the following way. We can say that the essential image is closed under colimits. Okay. How then do we prove our result? So let F be any element in the category of quasi-coherent sheaves on X. Now, as the T structure is right complete, we can write F as the colimit of its truncation, so the less than or equal to truncations. Now, by fact D, which is the proposition we just mentioned, that says that the int category of perfect connective sheaves is isomorphic to the connective part of, is equivalent to the connective part of quasi-coherent sheaves. Since each of these truncations will be, in some sense, connective, actually minus n connective, not properly zero connective, but whatever, I mean, each of these tau greater than or equal to minus n of F will be in the essential image of the theta we defined upwards, which was given by the int category of perfect objects. So we are removing, in fact, the connective requirement on the. Now the essential image is closed under colimit, so also F will be in the essential image of theta. So also F will be a filtered colimit of perfect objects, as we wanted to show. Okay. Before moving to the proof of the main result, we propose a refinement of this proposition we have just proven. Proposition we just proven in particular stated that the category the category of connective object was compactly generated. The refinement here proposes this other version. So let, as always, X be a qcqs spectral algebraic space. Then there exists a perfect sheaf F in quasi-coherent objects on X, such that the smallest subcategory of quasi-coherent sheaves on X that contains F and is closed under colimits and extensions contains the whole greater than or equal to 0 part of quasi-coherent sheaves. So we passed from having, as I said, this category to be compactly generated to have a single compact generator. And this will be essential in the proof of the theorem, which I'm recalling here now. So let X and Y be spectral Deligne-Mumford stacks with X qcqs a spectral algebraic space. Then there is a fully faithful embedding theta from the maps in spectral Deligne-Mumford stacks from Y to X to the symmetric monoidal functors from quasi-coherent sheaves on X to quasi-coherent sheaves on Y, given by the pullback, whose essential image is spanned by the symmetric monoidal functors preserving small colimits. And if you compare it to this proposition C, which now we know to be true because it depended only on proposition B and some other result which we give as granted. The only difference is that right T exact, as I was stressing. So how do we proceed? As I said, by comparing this with proposition C, the essential image consists of those symmetric monoidal functors f such that these functors preserve colimits and these functors preserve connectivity. They are right T exact. What we will show now is that in this setting, the first condition implies the second one. So let f be any symmetric monoidal functor that preserves colimits. Now, first of all, connectivity is something that can be tested locally. It behaves well with respect to gluing along open sets. So we can, without loss of generality, assume that Y is the Tal spectrum of some ring R, is an affine object. So that in particular, the category of quasi-coherent sheaves on Y will be just the category of modules over this ring R. Now the functor f is symmetric monoidal, so it preserves dualizable objects. This is just this is a standard feature of dualizable objects under symmetric monoidal functors. Now, by lemma A, we know that perfect is the same thing as dualizable. So f is perfect. So yeah, if we start from a perfect object, which unlikely I call still f, in quasi-coherent sheaves on X, this is the same as a dualizable object here. F is symmetric monoidal, so its image will be dualizable. So, by the equivalence, perfect if and only if dualizable, the image f of f would be perfect. Now, let's use the last result we proved before this theorem to produce an element f0 in quasi-coherent sheaves on X be a perfect compact generator for the greater than or equal to 0 part of this category. We also know that its image will be perfect, so in particular it will be minus n connective for some integer n, positive integer n. Now let C be the subcategory of quasi-coherent sheaves on X, the full subcategory of those sheaves F such that their image under the functor F is minus n connective. Now this subcategory C contains F0. Moreover, as the symmetric monoidal functor F preserves colimits, by assumption, well, not really by assumption, I mean it's one of the consequences of the theorem for perfect stacks. So the functor f preserves colimits, then this category C will be closed, in particular under colimits and extensions. So this category C contains the smallest full subcategory containing containing F0 and closed under colimits and extensions, which is nothing but which implies that it contains the greater than or equal to 0 part of quasi-coherent sheaves on X. So we have this this relation, let's say that I called star. So the quasi-coherent sheaves on X, the greater than or equal to 0 part of this category, embeds into C, which is sent by the functor f to the greater than or equal to minus n part of quasi-coherent sheaves over Y. What we want to show now, we're almost there, we want to show that n is equal to 0, so that connective part is sent to connective part. The functor is t, right t exact. So pick a functor f, a sheaf f in quasi-coherent sheaves over, in connective quasi-coherent sheaves over X. By fact D, every connective object is a colimit of perfect connective object. Filtered colimit. Now f preserves colimits, so we may, without loss of generality, assume that the f we start from is perfect. Now we set up a contradiction argument. Suppose by contradiction that f of f is not connective, so it will have some negative, some homotopy in negative degree. Pick in particular the largest m such that pi minus m of f is different from 0. There must be a largest m because of the fact that f is perfect. Now, pi minus m of f is a finitely generated module over pi 0 of r. Recall that we assumed that y was affine, so quasi-coherent sheaves on y is the same as modules over r. And let's use a most famous, I would say, result from commutative algebra, Nakayama's lemma, that says that that implies that there is a residue field K of R such that this homotopy group, this base change homotopy group, pi minus m of K tensor R of f is different from 0. Good. Now, if we replace f by a large enough tensor power, in particular the n plus 1 tensor power, we can make sure that this minus m is in fact smaller than minus n. So in particular, m is larger than n. I mean, we can push this homotopy downwards now that we are over a field. And so this yields contradiction, because we were assuming that f of f were in the minus n. We concluded that f of f had to be in the minus n connective part. And so what we conclude that n has to be equal to 0, so that f has only f of f has only homotopy in like the positive part. Good, we proved our theorem, and so we proved this Tannaka duality version for spectral algebraic spaces. Now one might ask, why do we care? Well, Tannaka duality provides implies some interesting results, and I'm just going to mention one to conclude. In particular, qcqs spectral algebraic spaces behave very nicely. Proposition, which is 9.6.5.1 in spectral algebraic geometry and is denoted as Serre's affineness criterion. Let X be a qcqs spectral algebraic space, then X is affine if and only if the global section functor gamma X from quasi-coherent sheaves on X to spectra is right T exact. Now observe that if we assume that X is affine, so we go in the implication from left to right, then the global section functor can be in fact identified with a module, with a forgetful functor from spectral modules over A to spectra, which is always T exact. So let's say that this implication is like immediate. It's the proof of the other implication that is like highly non-trivial and makes use of Tannaka duality. And this is all I had for you today. Thank you very much.
Thanks, Federico. So, do we have any questions for Federico? If that's not the case, let's thank Federico again. And we'll see you with the another talk on next week on Semiwa. Bye-bye.
Bye. Bye-bye.
Bye. Bye.